Okay, welcome to Photographic Technology, day one. We've got coffee and donuts in the back for anyone that didn't hear that already. And in future weeks, we may not try to bribe you that way. It's kind of futile trying to bribe Googlers with food or money, but we try. Thanks for coming. Today, I'm gonna start with kind of an overview of not the whole course curriculum, but sort of what I consider to be the front end part, the stuff about light and imaging and optics and sensors. And then there's a whole bunch of open-ended material that follows in terms of what you do with the images that you get out of a camera. We're going to try to cover this. This kind of front-end material is going to be the subject of probably a half a dozen more lectures when we get into depth in the different areas. And then there'll be another, at least that many, probably more on sort of the applications and back end and how do you handle and process and apply these digital images. We've got several volunteer lecturers signed up to help, and probably do half the lectures myself or something like that. Today I've got way more slides than will fit in an hour, so I'm thinking of splitting it up over today and next week, and it's still just an overview. We're not going to be going into depth in terms of how to calculate things with equations and so on, but we'll get to some of that in later lectures, because you do need to be able to do some of these calculations to make reasonable decisions about photographic system design and operation. So let's jump into it here. So photography is basically the art and science of writing with light, of recording patterns with light, and that's what it means. And light is a really magical substance that you have to understand, and so we're going to address its properties in terms of rays and waves and photons and so on. And you have to kind of approach light from all these different sides in order to do the things you need to do with it to understand and analyze photography. As to whether it works or not, human vision is the ultimate judge. When we make photographs, we generally are intending to make reproductions of an image that a human can look at. So the human eye is the thing we're trying to satisfy with all this, and that makes the problem extra complicated because the human eye and the human brain is a very complex system. So the technologies that go in between the sort of light in the real world and the light fields that we reproduce on a piece of paper or a screen for someone to look at, there's a whole bunch of technologies in between that's the subject of this course, and it's all under our control. There's no magic there, which is the point of this slide. Sometimes it looks like there's magic, and sometimes the magic really has very simple explanations, like my friend Steve Chung here, who likes to take pictures of eyeballs in motion and so on. And he really does take glass eyeballs and put them in motion. He's not faking this stuff up in Photoshop, and sometimes he turns the picture upside down, which is why the water's looking like it's going up. But the point is, there's no magic. It's all understandable. So we need to understand the technology, respect the physics, please our eyes, play some tricks, and have some fun. So I made up my own 3 laws of photodynamics. These are some of the concepts we're going to try to get across in this class. The first one is that even an ideal camera needs enough light to make a good photo. You can't make great photos in the dark. You can't make great photos with infinitesimally short exposure times and tiny apertures and insensitive sensors and so forth. You got to have enough light. That's fundamental number one, even for an ideal camera. The second thing is there's no such thing as an ideal camera. Well, there's an ideal that you can kind of define, but you can't ever build it in practice. And we're going to define that ideal and understand what it means so that we can analyze quantitatively how much light you need to make a good photo. And the third thing is that the closer you can come to that ideal camera, the better you are, of course. So the ideal is out there. You can't quite get there. It's like the pot of gold at the end of the rainbow, but it's something you can strive for. So we're going to learn how to do these computations in different circumstances, what goes wrong, what's not ideal about cameras, and what can you do to bound the problem. Part of the course is going to be me going off on historical tangents to explain why we look at things the way we do. And so the first of these is Johann Kepler, who a couple years after he was finished getting rid of Tycho Brahe with mercury poisoning, if you haven't read that book, that's a good one. He figured out a bunch of stuff about optics, and there were some long-standing problems at that time. This is before the discovery or the invention of the telescope. there were lenses around, but people didn't really understand imaging. They made images with pinholes and pinhole-type camera obscuras, and there was this perspectivist notion that had grown up in the field of art and painting. So people kind of understood the idea of rays going through holes and making images. But there were two big problems with this that people didn't understand that Kepler figured out. The first was, how come if you image something through a square hole or a triangular hole, you don't get a square image or a triangular image? And people had a lot of trouble with this, and they had this notion of a single ray from an object to an image being an important thing, but they didn't really have this concept of a bundle of rays, and they were quite confused as to whether light really propagated in straight lines as rays or not. And so Kepler took that notion of straight line propagation very seriously and analyzed what would happen if the hole wasn't a tiny little round hole. So he had like a little triangular hole, and he put rays through it and found that each point from the object would make a little triangular blur in the image space, but you'd still get a good image. You'd still get a round image of a round object. It just had this little triangular blur pattern around the edge that you wouldn't hardly notice. So he figured that out by taking the notion of light propagating in straight lines very seriously and literally, which other people hadn't quite done, and by taking advantage of the concept of a whole bundle of light rays as opposed to single rays forming an image. The other problem with pinhole imaging that Kepler analyzed at that time was the observation that several people had made that if you made a pinhole image and you looked at the moon with it, you could measure the diameter of the moon, get the angular diameter of the moon in the night sky. You could do that same measurement when the new moon was occluding the sun in a total solar eclipse. You could measure the dark disk of the moon against a bright background. Depending on which way you measured it, the bright moon against a dark background or the dark moon against a bright background, you got a different diameter. And they were really confused about why would the moon be changing its diameter. And Kepler was able to show that the moon is not changing its diameter. What you're measuring are the different edges of these little blurs that you get from your pinhole. And the pinholes were big enough and the measurements accurate enough that they were actually getting different enough numbers that they thought they had a problem. And Kepler kind of resolved all that. So this was the beginnings of geometric optics and understanding imaging. Kepler went on to do a lot of other good stuff, like he improved on the Galilean telescope and showed how to make a telescope with two convex lenses that would do a better job of imaging distant objects. He was able to draw pictures of rays to explain how imaging worked. And he was able to do all this before the laws of refraction were known. He didn't have Snell's law yet, so and I'll show you what that is in a second, but he estimated that when a ray of light went from air into glass, that the angle relative to the normal would be reduced by about a third. So if you had like 3 degrees of angle of incidence, you'd get about 2 degrees of angle of refraction. That kind of estimate, that 2 to 3 ratio of angles, was plenty good for analyzing all of optical imaging and telescope design and so on, until you got into subtle effects like spherical aberration. So he was frustrated that he didn't know the true law, but he had stuff that was good enough to make a lot of progress. Around the same time, René Descartes did a bunch of stuff. He wrote a paper. Is my sound gone? Did I kick my switch? You still hear it okay? It's still okay? Descartes published a book called La Dioptrice, and he had worked out Snell's law from Fermat's principle of last time. People say that he worked out Snell's law because Snell had already worked it out and told it to him, but he hadn't published it yet. So Descartes was the first one to publish Snell's law, but people think he got it from Snell, which is why they named it after him. But he worked it out differently. Snell had measured it. I'll show you what it is in a second. I think next slide. But Descartes was actually able to kind of rationalize and say where it came from, which was I forget exactly how Fermat got himself involved, but he had this principle of least time, which says that light going from point A to point B takes the route that's quickest. And if you use that principle, you can derive Snell's law. It's a good homework problem right there. a few years later, actually a few decades later, Christian Huygens went further and explained how the principle of least time can actually be derived from the notion that light propagates as waves with different velocities and different media. And the thing that's important to realize here is that the notion of light propagating as a wave is fundamental, and it has fundamental important consequences when you're doing photography and imaging. So this is where the wave, the nature of light going from rays understood in the early part of the 17th century to waves in the later part of the 17th century was a fundamental progress in being able to understand imaging systems. Unfortunately, it kind of got put on hold by a couple of centuries by Newton, who didn't buy into the wave idea at all. So it took a few hundred years to come back. So Newton thought light was particles, and that idea came back again with Einstein, and that's also fundamentally important to photography as we practice it today. So because when you have an image sensor in a camera, even if it's a piece of film with a bunch of little crystals of silver halide or something, it basically works by discrete light absorption events, photons, little packets of energy that cause some change to happen in a crystal. In a silicon solid-state image sensor, we basically can almost count the photons that come in by counting the electrons that those photons generate. That's what the ideal sensor does. Anytime light goes into the silicon crystal, a photon gets kicked up into a state where you can collect it, measure it, count it. And if you can count it with a fine enough resolution to say exactly where it is, not just how many, but how many in what location, then you get a perfect ideal image. As long as that location is split up finely enough compared to the wave diffraction effects, then there's essentially no loss of information. That's sort of how we're going to define an ideal sensor. The ideal sensor tells you where every photon came in with a resolution finer than the diffraction of your imaging system. These systems have noise. The ideal systems have noise because these photon absorption events are statistical. So this noise is called shot noise. It's the statistical distribution of a bunch of independent absorption events. The important property about light as particles is that every one of those particle absorptions is independent in the sense that it's not like there's some intensity, and if you've gotten 90% of them and missed 10% of them, you can count on the statistics of the 10% you missed. No, the statistics only depends on the number you absorbed, and we'll get into that in more detail later. So going back and looking at image formation, why not just use a pinhole camera? By the way, a lot of the slides here, I've just put together illustrations to talk about, in most cases from public domain sources. A lot of the public domain books off Google Book Search have provided images like this one, and a lot of the slides are illustrated from material off Wikipedia, which are all publicly usable, repurposable images. About half of those images in Wikipedia that I've used that are related to photography are images that I put on Wikipedia. So some of them are mine and some of them are other people's. But they're not mine anymore because I gave them away. A few places I've got illustrations that are not public domain, and I've tried to give credit where appropriate for those. So this is just a picture of a camera obscura. That means dark room, for those of you who don't speak old French or Latin or whatever it came from. You poke a hole in one wall and you get an image on the other wall from these light rays coming through. So why not make cameras this way? And the problem is that this is very non-ideal because you don't get very much light and you get a lot of diffraction blur. The diffraction blur depends on the size of the hole that the light is coming through that's making your image. And the smaller it is, the more diffraction blur you get. And with a pinhole, if you make that hole bigger to get less diffraction blur, you get more blur due to that effect that Kepler found, where you're blurring with the shape of the hole. If you put a lens in the hole, you can get rid of that by converging the rays. So the ideal camera uses a lens to converge the rays through a large hole to limit the diffraction blur and get a lot of light. You find lots of illustrations of this concept of imaging in the early photography literature. For example, this one by Hermann Vogel wrote a really nice book on photography, 1874, about the chemical action of light in photography. And he's got good lens descriptions and so on. So the upper image here shows a light coming in, a top ray coming in parallel to the optical axis and going to a point that defines the focal length, and then another bundle of rays from a object point propagating to the left to make an image point. So it's very simple. All you have to do is make lenses that converge all the rays from a point in the object to a point in the image plane. And of course sounds simple, but it's practically, it's impossible to do perfectly, and to do it ideally means that's something we can define and analyze. So let's see. So this is the notion of focusing, taking all the rays from a point, bringing them back together at another point. Hermann Vogel referred to that point as a Bildpunkt, which surprised me, because after I had spent about 4 years researching the history of the word pixel, and traced it back to the German word Bildpunkt, which is the German word for pixel in the original patent on television. I then found that 15 years earlier, Vogel had the same word in his paper on photography for an image point. Bildpunkt means a picture point. So he wasn't using it in quite the same way that we use pixels today, but he had basically the notion of an image point already. So when we think about ideal imaging, we have to think about what are the things that limit the perfection of your image. What limits the sharpness or the detail or the resolution that you can get in an image? In an ideal camera, you don't have infinite depth of field. Depth of field is the range of distances in the object space over which your image is sharp enough. Is my signal cutting out again? I'm sounding funny here. Yeah, let's see. Did I do something funny on this? Sometimes I hear myself funny and then I know it's not working. So you can think of a limited depth of field as a defect in a camera. That is, if things are further away from where you're focused, they'll be blurry. If they're too close compared to where you're focused, they'll be blurry. But I don't think of it as a non-ideality. I think of it as a property of the ideal camera, because you need some collection area in your lens to make an image, and that defines a cone of rays in your object space and in your image space that will give you a sharp image. That's an ideal situation. There's a trade-off to be made between how much light you get and how much depth of field you get, but that's all within a certain idealization of how perfect lenses work. Non-ideal effects are deviations from that. So even the ideal camera is limited by depth of field. And the ideal camera needs enough photons to make an image, and therefore it needs some time to collect those. So there's an exposure time. So the sharpness of your image is again limited by motion effects. If your subject is moving or your camera is moving during the 1,000th or 100th or 10th of a second or whatever it is that you collect photons, you're going to get blur. Again, that's not because your camera is not ideal. Even ideal cameras have that limitation, so we need to understand it. You get diffraction blur. Again, when you change the diameter of the lens to trade off the amount of light and depth of field, you're going to change the amount of diffraction blur as well. So it's the properties of light, the particle properties and the ray properties, the focusing and the wave properties. All these things are part of the idealization that causes the ideal camera to have limits. Loose signal again. Here we go. And finally, the shot noise. So the diffraction blur comes from the wave effects, the depth of field from the ray effects. The motion blur is a time that it takes to get enough light, and the shot noise is again having to do with enough light and the particle nature of light. So all of these ideal effects depend on all of the ways of looking at light as rays, waves, and particles, and we need to understand all those properties of light. Now, these cameras also have non-ideal properties. The note in the upper right basically says that more light always helps. So if you can take a given camera and increase the amount of light on your subject by bringing in extra lights or cranking up the intensity of the sun or not working on a cloudy day or putting a reflector in the scene or something like that, always helps. So it helps with this trade-off that you have in the ideal camera space. Non-idealities also can be helped by having more light in many cases, but things like the resolution of the sensor or the size of the grains in the film that you're using. The aberrations, which are the imperfections in your lens, the extent to which it's different from an ideal lens. The flare or glare or ghosting, which means the paths for light to scatter around, bounce off of your film, bounce off your lens, back to your film, things like that to create excess light that shouldn't be there. Other noise sources like electrical noise in the readout. When you're trying to count photons and your A to D converter is actually counting 5 or 50 electrons worth of noise, that's a significant non-ideality. So we have to understand all those kinds of things. Did I skip one? No. So in the front end of the camera, we want to study lenses and sensors. That's where all these effects of light come in. That's all the things we need to understand. We need to understand image formation by lenses, the limited depth of field, the motion blur, aberrations, flare, distortion. We need to understand the light sensing by silver halide and by silicon. We're probably not so interested in film anymore, so we'll focus on silicon. Distinguishing the ideal effects of shot noise in sensors from non-ideal effects, resolution limits, aliasing, nonlinearities, and so forth. And then we'll need to understand how to do color. I haven't mentioned color yet, but it's it's a huge topic to go from a really almost ideal refined black and white or panchromatic image sensor to then figure out a way to get color out of that. Introduces huge non-idealities into your system and a whole raft of new problems. And then, of course, all the practicalities of how do you capture the data off of the silicon? How do you store it? How do you process it? What do you do with it? So these are the kind of topics we'll be getting into. So that was the sort of first pass overview. Now we'll start going into a little bit more detail. If you want to take any of this stuff seriously, you'll want to have some books to refer to. These are probably the best two that I've found that cover a lot of this material on cameras. Again, not on applications as much, but on cameras, light, and photographic imaging. The Manual of Photography, this is the 9th edition. I've got all the other editions as well if you want to look at them, but the 9th one is the first one that includes digital as part of its content. So it says photographic and digital imaging. The one on the, it still doesn't have very much on digital. It's kind of new additions to these guys. But it's really good compendium of material accumulated over 150 years or so with some really top-notch authors. Sidney Ray there is, people make fun of his name because he's so big in ray tracing. He's written all the sections on ray tracing in the book. So, good guy. Ralph Jacobson, the current president of the Royal Photographic Society in England, and Jeff Attridge is a professor emeritus at Westminster University, and I don't know about Oxford. This other book, pretty recent, 2006 actually, is the copyright date on it. It has a whole bunch of really good chapters on details of what goes on in digital cameras and image sensors. It's got a little appendix in the back that'll let you figure out how to do all the calculations you need to figure out exactly how many photons you're going to get if you take a picture at ISO 100 with a normal exposure and so forth. It's got all those, it's got the numbers and the examples and all that stuff you're going to need. So let's start looking at the camera. What's a camera? It's just a box with a hole or a lens in it that images a scene onto a focal plane. So geometrically, it has some field of view, some width that's defined by the size of the film or focal plane in the back of the camera and by the distance of the pinhole from that plane, or equivalently the focal length of the lens. So it images some part of a scene out in the real world. Typical cameras image about like I've drawn here. It's what's called rectilinear imaging. So there's a flat plane out in the object space that images to a flat plane in the image space, and things on that plane retain their relative sizes. There's no distortion of size. That's kind of the ideal in most camera lenses. The alternative is you get some distortion. The extreme alternative, when you want to make a really wide-angle view, is lenses that give you extreme distortion, like fisheye lenses that'll map a whole hemisphere of space into a little circle. And you can't map hemispheres to circles without some distortion of the relative sizes of things, and that's what a fisheye lens does. So there's a big range between these rectilinear or non-distorting lenses and fisheye lenses that distort a lot. But for most purposes, we just think in terms of rectilinear, and we mostly think of magnifications just near the center, and we just sort of simplify away everything we can, because you can, by just looking at the center of the image, the focal length tells you about everything you need to know about how the object space maps to the image space. A camera has settings. Typically there's the traditional film camera has a shutter speed, an aperture setting, and a focus setting. And you can get plenty of old simple mechanical cameras, like these miracle cameras that still work even when there's no battery in them. That's what we're talking about here. But even the modern electronic cameras have essentially the same controls. This is a picture of a camera. This is like the one I learned on, camera that my granddad bought in 1922 to take pictures of my dad when he was born, Kodak Autographic Junior camera. And it's a piece of cake, and you can learn everything you need to know about photography from old cameras like this. This one has shutter speeds that you can see going from a 25th of a second to a 100th of a second. It's got these other settings marked B and T for bulb and time. You guys that have taken pictures probably know what that means. We might talk about it later, might not. Down at the bottom, it's got this aperture setting scale. This one goes from US 4 to US 128. And when I was a kid, the US scale was already about 100 years obsolete, and so I didn't quite know what that meant, but not quite 100 years, but 50 anyway. And it turns out that's a non-standard scale, but there's corresponding F numbers that people would use instead today. There's still a lot of old Kodak cameras that use this US scale, which stands for the uniform system, and at one time was the standard adopted by the Royal Photographic Society of London. These numbers are actually equivalent to F8, F11, F16, 22, 32, and 45, in case anyone needs to know. When you have a camera like this, you have to figure out how to set the exposure time and the aperture, and there's a lot of different ways and tools to do that. Nowadays on digital cameras, the typical way is you take a picture and you look at the response and see if it's too light or too dark and change it. So there's kind of a feedback loop that prevents you from having to think about it. But if you're designing a system, you're probably going to want to think about it. You're probably going to need to calculate how much light you're getting and how much noise you're going to get and so on. So there's lots of tools you can use to estimate the amount of light that's available in the scene that you can use to set your camera with. And this is one such tool. It's a two-slide boxwood and brass slide rule called the Herter and Driffield's actinograph. It has a cardboard insert. You can get a set of different inserts for different latitudes, and this will let you calculate the amount of light available as a function of the time of day, time of year, and latitude, which is pretty cool. And so if you're designing a system for outdoor photography, you might want to look at this. It's got an awful lot of information in it that'll help you figure out how much light there's going to be. More typically, though, what a photographer would do is say, well, bright day near noon, I'm not near the North Pole. There's kind of a standard amount of light. I know what that is. If I'm on a darker day or a higher latitude or bad season or something, I know how much to adjust it by. And you just kind of work this stuff out in your head based on your experience. There's rules like the Sunny 16 rule, which says set your camera at f16, set your shutter speed at the reciprocal of the ISO speed of your film, and it'll be about right for a sunny day, and adjust from there. The settings on a modern lens are essentially no different. This example of a Nikkor lens that has a focus setting and an aperture setting. The focus setting lets you read out the distance that the lens is focused to on a scale here. And it's got a bunch of other markings on it. So the lens is marked with its focal length, 35 millimeters here, the maximum aperture, 1 to 2, which means that the lens will open up to a diameter equal to 1/2 of its focal length. It's got the f-stop scale here, so you can set the aperture. This is the diameter measured as focal length divided by that number. And it's got these markings on the focus scale that let you tell for different f numbers what range of distances you should expect to be sharp in your image. So this is the depth of field scale. So there's a lot of complicated numbers on lenses, but they're all actually pretty easy to understand once you know what they're trying to tell you. And you can do these calculations for things like depth of field and amount of light corresponding to different F numbers and all that stuff quite readily. We'll get into a little bit of that. Here's what an F number is. We typically denote F number by the variable n, capital N, the n of a lens. And it's just the focal length divided by the diameter. This is the effective diameter, the diameter that determines how much light from the object space gets through the lens. It's, you'll find that that corresponds to the diameter of the entrance pupil when the lens is more complicated than the simple lens we've shown here. There are standard scales, essentially labeling by different conventional roundings of powers of square root of 2. The square root is in there because the area is doubling for each increment here. So since the area goes as the square of the diameter. How many people already know all this stuff? That's good, about half. That's about where I expected to be. So I'm going to, trying to drag the people that aren't totally familiar with it along, so we'll have some common terminology. There's a bunch of stuff you need to know about how to manipulate lenses. Lenses are generally specified by the curvatures, the radius of curvature of their faces. So that's what the R1 and R2 are in the upper picture here. But those are kind of the manufacturing details of the lens. You probably don't really need to know that unless you're designing lenses. But the behavior of the lens is specified usually by what's called the lens equation, which is this sum of reciprocal distances is equal to 1 over the focal length. So the distances S1 and S2 in the lower picture are the distances from the lens to these two conjugate points that are in focus with each other. So the points are said to be conjugate if the rays emanating from one point converge at the other one. So the distances at which that happens, S1 and S2, which are the distance to the object and the distance to the image, are related by this formula. The sum of their reciprocals is equal to the reciprocal of the focal length. You can also look at things like the ratio of those distances, and that's the magnification of this system. It's shown here with a minus sign because the lens inverts the image, so that means the magnification here is negative S2 over S1 if the object at S1 is imaged at S2. That ratio of distances can also be expressed in terms of the focal length and one of the distances, as is shown here. So this is a pretty handy thing to use sometimes. If you're doing close-up photography, magnification is something that matters a lot. If you're shooting things that are off at a nearly infinite distance, your magnification is essentially 0. You don't usually express it in these terms. You would express it instead maybe in focal plane distance per angular measure or something like that. That doesn't have that infinite distance factor in it. This is one of my favorite old opticians is Moritz von Rohr from the what was it called, the Carl Zeiss Works in Jena. These guys worked out a lot of really great modern optics in the late 19th century that's still very relevant. This particular one is how to think about calculating the depth of field. If you've got an imaging system on the left here, where I've shown kind of a box for the camera with an image in the back of it, but I haven't given you the parameters of the box. I haven't told you how big that image is, or what the focal length is, or what the F number is. Turns out you don't need to know any of that to compute the depth of field. And that's what von Rohr showed in his method, is that you can just look out here in the object space, and if the camera is collecting light from an aperture of some diameter, you can, and it's perfectly imaging some plane, some object plane out here into the image plane, you can figure out how much blur any point in the object space has by projecting that point with these cones into this plane, and then see how big the blur is in this plane, and then image that. So if you can define how big an acceptable blur is at the object plane in terms of some angular tolerance E times the distance to that plane, then you can calculate these points where anything closer than here would make a circle bigger than that, anything further than here would make a circle bigger than that. So the range of things that are in focus are from this near limit to that far limit, which you can trivially work out the algebra from this geometric picture. And this is in contrast to the way people normally work it out using the lens equation and working it out inside the camera in the focal plane in the image space. With this method, you don't have to use the lens equation at all. All you have to do is figure out what your tolerance, your angular tolerance E is, and this becomes a very simple method. So I'll say more about this and also other applications of the outside the box concept. So without knowing the focal plane or the size of the size of the focal plane or the focal length of the lens or the F number of the lens, just taking the box as a box with a hole in it, you can work out the diffraction limited resolution at the object. You can work out the depth of field at the object. You can work out the number of photons collected from the scene and how much exposure time it takes to get an ideal camera to make an acceptable picture of that object. You can do all that outside the box just from knowing the diameter of the lens. There's a question, yeah?
I mean, your argument suggests that the depth of field is dependent on the resolution you want to have in the sensor, because if you have higher resolution, you want a smaller, and that's not what the scales tell us. They seem to be...
Okay, the question is that my argument suggests that the depth of field that you calculate this way depends upon the resolution that you're trying to get out of your optical system. And that's absolutely correct. And the other part of the question was that's not what these scales show you. If we go back to the scales on this lens, there's no way to put your opinion of how much resolution you want into the interpretation of these depth of field scales on the lens. And that's correct. These depth of field scales on the lenses are based on somebody else's opinion. So if you have a different opinion, these are generally based on, most conventionally, the idea that the diameter of the blur circle in the focal plane should be no bigger than 1/1500th of the diagonal of your image. That 1/1500 number has been fairly consistently used for the last 25 to 30 years, and earlier than that, typically slightly laxer numbers were used, like maybe 1/1000th. So if that's not the resolution you're aiming for, you have to adjust your interpretation of these distances. And if you want twice as much resolution on this scale, you just want to get you want to cut the distance in half, twice as close together. Yeah, another question?
So what's always confused me is why the f-stop scale is used as like a linear measure of the lens, when most of the things you're interested in are area related. So why don't we use a scale that's aware of that? Because it would give you much more. Give you much more useful information.
Excellent question. The question is, I don't mind taking a lot of questions. So I'll go into this. I got plenty of time in coming weeks to go on. So let's stop and talk about this, because it is a very interesting question. The f-stop scale is a linear measure of the diameter of the lens, but the amount of light you get through goes like the square of the diameter. So why don't they use a scale that's more like the square? And there's several aspects to this. So the one is the F number scale is a very natural thing to define. It's non-dimensional. It's a ratio of distances, so you don't have to put any units on it. If you go with a measure of the area of the aperture relative to the focal length, you have to decide how you're going to measure that. So now you're going to have numbers that either have some arbitrary scale factors in them, or you're going to have some distance units in them, or whatever. If you go back to this Kodak camera, the US scale, the uniform system, was adopted specifically for the reason you're asking about. The numbers here are proportional to the amount of exposure time you need to give the image. So when you open up by one stop from 16 to 8, Instead of exposing for 16 seconds, you can expose for 8 seconds or milliseconds or whatever. So that was the purpose of those scales, but these scales were very unintuitive to compute things other than exposure. You couldn't easily look at the diameter of a lens and the focal length of a lens and know what its US number was. You'd have to compute its F number, and then you take the ratio and then you go through some mapping to figure out what it is. So both systems have some merit. The F number scale is also it's easy to get from these simple measurements, and it's non-dimensional, and there's no table mapping you have to go through or arbitrary steps to define it. And because it represents the diameter of the lens, it represents the sizes of these ray bundles and these angles, which lets you do a lot of very direct calculation of things like the depth of field and the angles and so on. Let's see, here's some, did that answer your question? Yeah. So depth of field is really important, and it's the thing that limits how you use an ideal camera very often, because you have to get enough light, but you also have to keep your subject in focus, and there's always this tension between getting enough light with more time or getting it by a bigger aperture diameter that causes things to blur more. So historically, there have been a lot of different ways to calculate depth of field, and these are some of the analog computing devices people have used. Kodak put out a lot of these books of data books that they were big on these little circular slide rule computers. The one on the top here is the depth of field scale for wide angle lenses, and the one on the bottom is the depth of field scale for telephoto lenses. And they had a bunch of different settings in here where you could set a combination of a focal length and a film format, and then you could look. You get different F numbers showing up in little windows here that let you take a range of distances here, and fascinating little devices. I have this straight slide rule that lets you do a similar thing by you pick your combination of your lens focal length with your aperture and put it against this mark here, and then on this scale you have aligning with each other all the corresponding near and far distances. And it's the same kind of thing you get on lenses themselves, where you've got these aperture scales. Now, most of this stuff has disappeared with digital cameras. Most of the lenses nowadays don't have the depth of field marks on them anymore. And you're kind of shooting blind, or you take a picture and you look and see if it's sharp enough and then change it if it's not. But if you're designing a system, again, you have to be able to compute this stuff. If you're trying to image high-resolution book pages from a camera and make every page sharp, even as you turn pages and they get closer and further, for example, you have to work that out. And so that's why we're going to be talking about it. The other thing that's really important in photography is this notion of tone, or tone rendering, tone scales. The idea that different amounts of light and dark get turned into reproductions of light and dark on some scale that doesn't necessarily bear a simple objective relationship to the original scene. And this is often overlooked in digital photography. There's a huge history here, and yet people will often kind of assume that's irrelevant and kind of assume what's called objective tone mapping. So the assumption that you want in a reproduced photograph shades of light and dark that are in the same ratio of the shades of light intensity in the original scene is a bad assumption. Don't make that assumption. So we want to study this notion of tone rendering. And this picture from Kenneth Meese's book on photography. He was the head of research for Kodak for many years. Talks of what he calls the cycle of tone reproduction that has to do with scenes and negatives, and developing negatives to different contrast ratios and printing them as positives and viewing them with the eye and illuminating them and viewing them and so forth. All of these steps of illumination and eyes and development and printing, all these things are important in determining what the tone reproduction scale looks like. And there's many different ways to get from over and underexposed negatives to decent looking prints, but they don't come out looking identical. They have different tone scales that aren't gonna reproduce very well here, so let's don't look at them too closely. But it's not just a question of how do you reproduce a given tone scale, or what can you reproduce, or what are the non-idealities, but the huge question is what is preferred, what looks good. So that's been studied a lot, and vision is a non-trivial and non-linear sense. So the preference is a very subjective thing. And this shows 3 different examples of the mapping from the subject luminance, the original scene, to the optical density of a reproduction. Density is a term that's often confusing. Originally came from Herder and Driffield, who the guys that did the actinograph. They were the guys that sort of founded the whole science of photographic densitometry and sensitometry. And density to them meant the amount of silver per unit area in a developed photographic image. So it's a literal density. It's like how many micrograms or grams per square centimeter or something like that. But optical density, which is fortunately pretty much linearly related to the literal physical density, is a measure of the transmission or absorption of light. And a higher density, one density unit means a factor of 10 loss of light. So if you illuminate a print and you get a reflection of 10%, that's an optical density of 1. Or if you illuminate a transparency and you get a transmission of 10%, that's a density of 1. If you get a transmission of 1%, that's a density of 2. So this vertical scale D is a logarithmic measure of objectively measured light coming out of your reproduction. And the horizontal axis is a logarithmic measure of the objective amount of light in the original scene. The dashed line would be what we call an objectively accurate tone reproduction, and the solid curves represent the kinds of tone renderings that are found to be preferred typically in photography. In a typical reflection print, the slope of the preferred curve is a little bit greater than unity in the middle, which means you want a little bit of extra contrast in the midtones of your print for it to look good. And you want it to be smoothly compressed toward dark and light on the 2 ends. You don't want an abrupt clip. And you want it to be a little darker on average than the original scene. And the reason for that is that I'm sorry, that's not darker, that's lighter. You want it to be lighter than the original scene, because in the original scene you tend to have things like light bulbs and sunlight coming through windows. You get a lot of kind of bright spots that you don't really care about. Everything else is relatively dark. On a photograph, you want to take all that relatively dark stuff, that's where your subject is, and brighten it up. So lower density. And so that's kind of what's generally preferred. But if you're viewing a slide in a dark room, a transparency, this would be in a dark room, and this would be in a kind of viewing on a viewer in an average lighted room. You get, again, different preferences. With transparencies, there's an even greater slope in the middle, meaning you really want more contrast for the thing to look good. And you really want it to be darker, because otherwise it looks washed out when you're viewing it with projected light. And so you have to look at how these things are being reproduced to figure out what kind of tone scale you're after. Yeah?
How do these curves relate to the curves and level dialogues in Photoshop?
Good question. How do these curves relate to the curves and levels dialog in Photoshop? It's a complex relationship because in Photoshop the scales that you're working on are not log luminance. They are gamma compressed intensities of reproduction primary. So it's a different kind of nonlinearity, but the same kind of curves are important, but they don't quite look the same. They still should be somewhat S-shaped, but the question is compared to what? So you don't generally have in Photoshop any measure of the original log luminance of a scene unless you're working with raw data, in which case you might. Yeah, another question back here.
Which one of these curves relates to a LCD or CRT monitor?
Yeah, and how do these curves relate to what the monitor does? And that's another good question. That's part of that same thing. And when I mentioned that Photoshop, you're working with gamma compressed intensities, that's because the whole notion of a gamma comes from the original behavior of cathode ray tube monitors, where the the current coming off of a hot cathode responds nonlinearly to the voltage you put on it, and that's sort of the origin of the use of gamma in television representations that led to computer representations. But there's actually much better reasons to use a gamma compression curve, and I'll explain what all that is. The outline for the course mentioned that there's like a whole module on gamma, because it's a huge important topic and hugely misunderstood. I know that's not an answer exactly, it's just deferring the question to a later time. So film is nonlinear. The term gamma in photography is used a lot in film, and I don't know if it originated there or if it originated in the television technology. I'll have to look into that. But the gamma is the slope. All of these curves that I just showed you, you can measure the slopes at different points. And the slope in a log-log space like this is called gamma. Because of the way density is defined, these curves are headed downhill. You may typically want to look at it the other way or use the absolute magnitude of the slope. But basically the slope is called gamma, and when it's greater than 1, that means you're increasing the contrast, or your reproduction has more contrast than your original. Film has this too. This is called a Herter and Driffield curve, H&D curve, or a D log E curve. It's a plot of density versus log exposure. And these curves for typical films have what they call a straight line portion in the middle, and the slope of that straight line portion is what's typically called the gamma of the film. You can actually measure gamma at all of the other non-straight points as well and plot gamma as a function of log exposure and so forth. You have a lot of control over these numbers, these gamma numbers, and that's one of the things that Ansel Adams taught in his whole system of photography based on zones and so on, is that you control the gamma. How long, the time and temperature of development of your film determines the gamma that you're going to get out of it. You have a lot more control in developing your film negative than you do in your print. So you want to do a lot of that work up front when you're composing the picture. Figure out what kind of contrast you want in your scene and develop it appropriately. We don't have to do that with digital cameras. We can do all this stuff after the fact because the sensors tend to be pretty inherently linear. So once you've got a negative and you want to make a print from it, you stick it in your enlarger and you project it on sensitive photographic paper. This is a cool device. I bought one of these Kodak home enlargers off eBay a few years back because it has on the back of the easel a little circular slide rule for computing exposures and enlargements and everything. And I collect slide rules, so I had to have it. But so I had to show it to you. But the point is that when you go through this process of taking pictures and developing negatives and making prints, each of those steps does something to the tone scale, and you can cascade these nonlinear functions with what's called a Jones diagram, named after Lloyd Jones, who used this as a method for studying and explaining tone reproduction back in the 30s. And depending on what steps you want to illustrate, you may have 1 or 2 or 3 or 4 of these quadrants, and you can map around a circle with this and end up back in the luminance space to compare an original objective scene luminance with a reproduction, which is what this one does. So this quadrant 4 here is the reproduction. You can see how he's getting an S-shaped curve that matches the preferred reproduction by controlling the gammas and the nonlinearities of the negative and the print, and you can put different functions into these quadrants depending on what you're trying to do. You can put in a perceptual model of what the eye does to see if the subjective reproduction then comes out looking like the original scene. So you can kind of close the loop on whether you've reproduced the perception of the scene by modeling perception if you want to. That's a little harder. So we might look a little bit more at these kind of things. I didn't get as far as I wanted to today, but I'll spend a few more minutes. I want to get into a little bit more about optics now and talk about how rays of light are refracted by lenses. This is just a picture of a little It's called a cylindrical lens because its surfaces are only curved in one dimension instead of two, and these are good for making science fair projects and so on and illustrating light refraction. But in photography, we use spherical lenses. For example, this represents a globe of glass that would focus light. This guy, Ibn Saul, Arabic guy, as you can tell by his writing, looks like we lost something here. He analyzed the refraction of light back in I think 984 AD and wrote it up. And he was working not on imaging so much, but on making burning lenses, so you could use the power of the sun to burn things. And the little figure in the top right with lines, I've reproduced over here approximately to illustrate what it was that he was figuring out. There's an incident ray, which he's drawn the distance from a point where the ray is incident on an interface between air and glass. This distance L1 to some normal line that he's drawn off to the side in some arbitrary place. And then there's a refracted ray which is extended back to that same line, and the distance L2 is measured. And what he observed is that if you do this little construction, then the ratio of L1 to L2 is a constant. No matter what angle that ray of light hits that glass, the ratio of those two distances is constant. This is in no way intuitive, and it was an important fact that got lost for about 600 years till Snell rediscovered it by essentially the same construction. And this constant ratio of distances can easily be recast with a little bit of trigonometry into the ratio of the sines of the angle of incidence and angle of refraction, which is the way it's normally represented today. But in fact, Snell, who got his name on the law, drew the same picture that Ibn Saul did 600 years earlier, or 500 and some anyway. So this is at the time, it was not easy to understand. There was no good reason to believe that the sine function had some magic to do with light, or that this ratio of distances had some magic to do with light. It was just something they observed by a lot of painstaking experimental measurement. They wanted to understand what the relationships were between these angles, and this is the best they came up with. But it turns out this is easy to understand once you go through what Huygens did and you understand that light propagates as waves. And there's this notion called Huygens principle, where each point through which the wave is propagating acts as another source, and you get these little, as if there's spherical waves coming out from every point, and they interfere with each other. And when they interfere in phase, the light keeps going, and when they don't, it sort of cancels itself out and nothing interesting happens. And Huygens drew a bunch of pictures to illustrate this effect. For example, these are wave fronts from different points where these wave fronts hit a surface. Each one of those re-radiates at a different velocity, and where these wave fronts are all in the same phase, you get a wave front moving on this way, and you can compute the angles of things from that. You can compute it from the principle of least time, which is what that picture was about. You can draw it as the ratio of these distances, which are the sines of the angles. So Huygens was able to explain where this law came from in terms of a physical model of light. So this was really, he was really the first guy that figured out how to model light physically to explain what's going on. He also figured out how to compute the shapes of lenses that would converge light from a point perfectly to another point within this law. Within what the law says will happen, he can compute the exact curve, and it's not spherical. And he also did a lot of work on spherical lenses, where he says we can make spherical lenses because when you grind two things together, spherical is the shape you get. Any other shape is essentially impossible to make, and that's still true today. Most lens surfaces are spherical because that's what you can grind. So he said, given that constraint, that's what we can make, how do they behave? And so he was able to work out and characterize what's called spherical aberration. He was also able to show that if you have a spherical surface, you can correct its aberration by an aspherical surface, and again, converge light perfectly to a point. This is all in the 17th century. You don't have to necessarily understand all this stuff as deeply as Huygens did, but his little book is actually a very fun read, and I'll recommend that one too. I have a library of books that we'll talk about from time to time and let you guys borrow them and read them if you like. And let's cut it off here, and we'll continue this next week. Thanks so much for coming.